Hello? Can you hear me?
Yes.
Yes.
Hello.
Okay, so welcome back. So first, let me remind that the homework 2 is due Sunday. So last time we talked about using Qiskit, and today we're going to tell you more. And we're going to discuss the circuit model of quantum computation, quantum gates, and then I'm going to show the gates in the Qiskit in the Jupyter notebook. But before I continue, are there any questions? Okay. So let me give really a sketch view of quantum computing in this so-called circuit model. So the idea is that you may want to run some quantum algorithm, and the quantum algorithm is written in terms of some unitary transformation. So maybe you want to take this through some unitary. Okay, and at the end you have to perform measurement, and that's what's stated here. So first, qubits are initialized, for example, all in the 0 state, and you want to run a really large unitary on the n-qubit. So in principle, this is 2 to the n by 2 to the n matrix. Okay, this is a very big matrix size, and a mathematical result is that you can decompose this really big unitary matrix into smaller building blocks. So I indicated that the building blocks are 2 qubits together, so like 2 qubit gates. And this is just an illustration. I sort of separate those in a sequence of 2 qubit gates, and I call it round 1, and second round you can do similar applications, etc. But at the end, you measure the outcome. So it's usually this symbol, you read out whether 0 and 1, you read out for all the qubits that's needed to read out the results. Okay, so that's really the basic standard circuit model. So the 3 steps: initialization, gate operation, measurement. So we're going to talk about gate operation more and a little bit measurement. So for gates, the math theory says that you can decompose such a big unitary, n-qubit unitary of size 2 to the n times 2 to the n into really just a sequence of 1 qubit and 2 qubit. So I'm indicating, even though I indicated 2 qubit, but in fact you can regard 2 qubit gate. 1 qubit gate is a special case of 2 qubit gate. So 1 qubit gates are represented by a line with a box that acts on that particular qubit. The set of universal gates in the 1 qubit sector include the Hadamard gate that we have seen, and the T gate. T gate basically transform non-trivially on the 1 state where there is a pi/4 phase shift. Okay, and there's also a S gate, which is the T square. That matrix is really just R1 and I in the diagonal elements. So the non-trivial gate that need to have involving 2 qubits, you only need one, and one particular example is the CNOT gate that we have seen before. which basically is using this 4x4 matrix. You have a block which is identity, the other block is X, and you can also write it in terms of this projector. If the first qubit is in 0, you do identity on the second qubit, or if it's 1, then on the first qubit, you perform the X gates on the second qubit. So this is the CNOT gate. So yeah, so the upshot is that you only need to have these 3 gates that can be applied anywhere. So the CNOT should be applied between any 2 lines, but this can be reduced just to nearest neighbor lines by swap. And they can be used to create such a big unitary matrix, at least to whatever precision that you want. So that's really the upshot of standard model of quantum computation and universal gates. Any question? Okay, if not, the next slide, I actually give more detail of the universal set of gates. In the previous slide, I said that for those 3 gates, you can use to approximate a big unitary as accurate as possible, but it's also possible to have the so-called exact universality, meaning that this U is decomposed into sequence of 1 and 2 qubit gate. This is exactly the same as the original. So to do that, you have to have arbitrary 1 qubit rotation. So we'll talk about more of the detail, but it's basically a rotation, arbitrary rotation in the Bloch sphere. So for example, the Bloch sphere, the U3 basically you take to any, so basically any rotation. Okay. Unlike the previous slide, this is approximate. Here, approximate. In a sense that we only use discrete, but you can make the error as small as possible. To have exact universality, these cannot be just a single angle. You have to allow arbitrary rotation. Basically, there are 3 rotation angles, theta, phi, and lambda. So I'm going to go to the detail of this particular gate later. But in order to have exact decomposition, you need to have this arbitrary 1 qubit rotation. But the CNOT is still the same. You only need, for the 2 qubit gate, you only need 1. So that's the CNOT. And this is the CNOT acting with the first one as control. This is the second bit as control. Yeah, you've seen this also in your homework. Okay. Yeah, so this I already mentioned. The approximate universality is you being able to approximate as close as possible. If you include more terms, then you will be able to approximate that. So I already talked about this. This is the first example that we've seen, but it's not the only set. You could use other sets. For example, you use this control almost Hadamard, right? Hadamard times Z gate. This is control Hadamard Z. And the swap. Swap basically, you can do it physically, just exchange the 2 qubit. A goes A, B goes the other side. You just swap the position. So you could also do the universality, so meaning decompose that big unitary in terms of just the W gate and the swap gate. Or the third set is you use Hadamard and a 3-qubit gate called Toffoli gate. So if you are a student of computer science, you may have heard of this Toffoli gate in classical computing. So you only need to have these two. That would also be sufficient. So it may be depending on physical realization. Some of the gates are easily implemented. Okay. Any question on this slide? Okay, so next I want to talk more detail about gates, and there are some identity between them. So for example, we talk about the basis transformation between the 0 and 1 to plus and minus 1. This is given by the Hadamard transformation. Basically, the mathematic is H transform Z by conjugating is X. So remember, H dagger is H. H squared is 1. So the equation here basically says X, you first apply X, and then you apply H equal to when you first apply H, and then you apply Z. So unfortunately, the diagram starts from the left. So the first gate you encounter is X. That's why we write in the to the right, because in terms of matrix, this is the first action that apply to a column vector, and then you apply the H. Okay, and this is the same equation. Okay, H times X equal to Z times H is equal to H times Z times H equal to X. So they're the same. Okay. So there are a few other identities. For example, one that includes CNOT. CNOT, if you want, let me just write out what it means in terms of mathematics. So the first bit 0, you do identity on the second. The first bit 1, you do the X on the second bit. So because Z is diagonal in this 0, 1 basis, so it commutes with 0 and 1. So you can actually push this behind the CNOT gate if the Z is on the first qubit. But if the Z is on the second qubit, in this case, this is identity on the first qubit, Z on the second qubit. It commutes with identity, but it does not commute with Z. So when you push this to the right, you need to compensate the fact that X and Z anti-commute. So you need to put a Z gate. So this is an identity. So V1, the mathematic is that 1 times Z, so you can regard this as 1, and that's Z. C0 equal C0 Z tensor Z. That's the mathematics. Okay. So in terms of X gate, it's sort of the reverse. If you have X gates on the first qubit, if you want to move past the control NOT gate, you move past that, but you also need to compensate by additional X gate But if the X gate is on the second qubit, because the CNOT has an X, an identity, they commute with X naturally, right? So you can move the gate to the right. So these relations are very useful. Sometimes you want to simplify the gate operations. Maybe they can push to the one side and then combine with the other parts. So such identity are really useful. Okay, and it's useful also in terms of visualization, that you see the mathematical identity in terms of a diagram. Okay, so that's the gate identity. And if you have things that involve with the control gate, and for example, here you have a control U, so control U, you apply V gate. This is on the second qubit. So if we want to be more rigorous, we should use identity tensor product V, and then control U, and then identity tensor product the V dagger, which is the same as its control V dagger U V. The gate that apply when it's control is V dagger U V. Of course, it's just also the same if you put you put B also in the control line. Okay, but it's interesting that you don't need that, then it's the same. Okay, this is particularly useful when you consider the control knot. So control knot, this is the control knot. I just write it explicitly in terms of X conjugated by H. So as we've seen before, becomes Z. So control knot turn into control Z gate by Hadamard. Okay, so this is control Z. Sometimes you just put two dots and a line linking them. That's the control Z. Okay, and you've seen this from your homework, the swap gate, right? So swap gate, physical swap is this, can actually be decomposed in terms of CNOTs in this fashion. So CNOT and reverse the order and then back to the original order. Of course, you could also write in this way. Okay. And you have verified this in your homework. One interesting one is the control constant phase. So you have a control, but it's almost identity except there's a phase, meaning that if this one is 1, then there is a phase applied to the second qubit, okay? But if this one is 0, then it's just 1, okay? So how do I understand this equality? This says that a control phase shift is equal to a single action phase gate on the control bit. So how do I understand that? So this is easy to see that. So if we can just see that if the first bit is 0, then it does nothing, right? If this if the first bit is 0, then nothing is applied. So that means if the first bit is 0, that's here, it's 1. If the first bit is 1, so if, let me just erase that. If the first bit is 1, this is applied. This e to the I alpha is applied. But I can put a phase back to that. It's really similar to the phase kickback that you have seen. So meaning that if it's 1 meaning this block, I have a phase e to the I alpha. So this is also a useful circuit identity. Is anything, any questions? Are there any question also in the chat? I cannot see the chat from my end. Okay, if there's a question, please shout out. Okay, so I'm going through a lot of the technical things that might be useful in designing circuit. So one of very useful one is this control U, right? So it might be possible you want to control operation, but this U is not necessarily CNOT gate. So how can we implement that? So there is a interesting identity, so mathematical identity, saying that if you can write U in terms of a product, it's almost A, B, C, but this A, B, C, the product is identity, but if you can insert X in between, if U can be decomposed into a phase, and then A times X times B times X times C, if you can find that relation, then the control U can be implemented using the control NOT gate. There are 2 of them, okay? And these A, B, C are sandwiched in this way. So basically C apply first, X, and here is control X, and then B, and then control X, that's where the X is. Then you apply A, and remember this is the phase, right? U1 phase that I have here. I'm basically using that already here. The overall control overall phase can be just written as a single phase gate on one of the control qubit. Okay. Yes.
But this control you only acts on 1 qubit.
Yeah, this only acts on 1 qubit.
We cannot generalize it.
Because this has X, right?
Oh,
if you want to generalize, you have to generalize the X, which is the multipartite, more qubit X, right? Because we use control X.
Yeah, that's right.
Yeah.
Okay, thank you.
Okay. So how do we understand this? Yeah, to understand this, we just check, right? So when first qubit is 0, right? When first qubit is 0, the circuit basically says the control does nothing, meaning that the circuit becomes C. There's no X because the control bit is 0, and then followed by B, and then A, right? Yeah. And there is also this U1, but U1 phase acting on 0 is still 0. There's no additional phase. It's only have a non-trivial phase when the bit is 1. And we see that this is identity. That's the requirement. Okay, so when first bit is 0, the action on the second bit is basically identity. When first bit is 1, then we can look at the effect on the second qubit is you have a C gate, the X gate is applied because there's a control, then B gate, and X gate, and A gate, and also the phase, e to the I alpha. And according to this, it's really the U gate, okay? Yeah, so this identity or this particular decomposition is useful to construct general gate if I'm only has control NOT, but I can actually use that combination to design any control unitary. Single qubit on the second, yeah, this is single qubit U, okay? Yeah, we can also extend this a little bit to the 3 qubit case. So for example, if I want to get this control U, basically this notation means that you use action if bits 1 and 2 are 1. Okay, so how do we see this? This is shown on the right hand side. Okay, so let me just say it. If the first 2 bits are 0, 0, 0, 1, 1, 0, the action is identity, but the non-trivial is if it's 1, 1, then you have a U. Okay, that's the meaning of this gate. Okay. So to understand this decomposition, we just have to go through what we did here for the 1-bit control case. So here we use 2-bit to control. So we need to verify that the right-hand side is the correct one. The condition is the V that I use here square to U, okay, and B dagger is its Hermitian conjugate. And additionally, I use the control NOT, okay. So the application of this is if I want to design a Toffoli gate, control X gate, for example. So we see the Toffoli gate appear in this third example of universal gates. So that one possible application would be that. Okay, now we check this identity. So let's check the identity. So if first bit is 0, if this is 0, the second line here, this you still have, okay, the second, third, you still have control V. This one does not activate, and this one V dagger, and this one is not activate, and this one is also not activate as well, right? So this is identity. It's control V and it's dagger. So unitary matrix V dagger is identity. Okay. Okay. If let's say if second bit is 0, okay. If the second bit is 0, then let's see the effect. If the second bit is 0, this does not activate. So this does not activate. And this one may activate. So the second 0 control NOT may activate depending on the first bit. So if we don't know what it is, we cannot say anything. So maybe what we do is let's check a case when first bit is 1. Let's go back. So if first bit is 1, okay, if first bit is 1, let's just show 2 and 3. If first bit is 1, if this is 1, then control NOT will activate on the second and this is control V. So I have not specified the second bit. And I keep going. This one is control V dagger. And this is activated. So there's an X here. And there's also a V here. Okay. So I want to analyze if the second bit, so we check this condition. We check both. I think we check these two. We want to check this condition, 1, 0, if the state is 1, 0. Wait, sorry. Yeah, this is 0. This represented 1, 0 is the first bit 0, second bit 0. Sorry, first bit is 1, second bit is 0. Okay. And we want to show that the action on the third bit is identity. And we also want to check 0 should return to 0. Okay. So 0 goes through this, X flipped to 1. 1 is flipped back to 0 by X. Okay. So it returned to 0. But the third qubit, the action, this is 0. So B does not activate. Here it's 1. So B dagger get activated. And when it flip back 0, it return to 0. And at the end, there's a B. So this is identity. Okay. Now, the only case that's left to examine is this final 1-1 case. This means everything activate. So the 1-1 case. So everything activate. So we can just draw this one. The first control V, the V is going to activate. And there's also X. I want to just identify the X where it's activated. There's a V at the end activate, sorry. So this one, if you start with 1 and control knob flip to 0, the second V dagger does not activate. So that's why I did not draw V dagger here. And if it flip back to 1, okay, so 1 here. And we see that the upshot of the action on the second qubit, the third qubit is B squared, which is U, right? Because we use this condition. So we verify the whole circuit. It's kind of lengthy to check this, but this is how we do that. You could also use matrix multiplication, but that's maybe even more cumbersome. Okay. So as I said, this can be used to implement the Toffoli gate. And we just need to find what square to X gate. And you can verify yourself that this V here, 1 plus I X, is square to X. So, I mean, it's easy to show 1 plus I X square is 1 plus 2I X plus I square X square. Okay, but X square is 1. I square is minus 1. So this cancel that. You're left with 2IX. So it's proportional to X. And this factor here take care of the 2I. So that V squared to X. And that's how you can implement Toffoli gate. I want to pause to see if there's any question. Okay, there seems to be something in the chat.
So you said we can achieve any quantum gate. You mean universal gate?
Yeah, so universal gate is if I go back, if I have a really big matrix U, I can sort of decompose in this way, and every block is either 1 qubit or 2 qubit. That's
But
what
what
I said.
about phase?
Phase can
The
also,
phase is not discrete.
I'm not sure what I mean by phase. You mean,
By using quantum gate, we can only get a discrete set of universal.
yeah, so if it's discrete set, if you have a discrete set,
Yeah.
then you can approximate. You can only do approximation. The accuracy depends on how many sort of levels of approximation you use.
So
But
yeah,
if you want, go ahead.
We can approximate any phase shifting gate
Yes.
with any phase.
Oh, you can approximate with just H and T, and then control NOT.
Okay.
You want a single qubit phase shift, or you want arbitrary, like some diagonal with phase?
Just some single phase shift.
Yeah, single phase shift. Yeah, here you can use H and T. You only need to
I
have
know the
H and
idea.
T.
Thank you.
Yeah, it's roughly, you can see that this is rotation in the Z, but H, it take you to Z, and then if you have rotation in X and Z, you will generate other rotation, and that rotation angle is actually not multiple of pi over 4. Yeah, you'll be non-rational of pi, and that you can use to sort of approximate, right? For example, if my gate, this just represents 0 to pi. If I can only have pi over 2, and the dot that I can have is just multiple of that. But if I can generate some angle, which is, let's say, I'm just writing randomly square root, then I could do this square root many, many times. And in the end, this will fill the interval, right?
Yeah.
So this is the idea of approximation.
Yeah.
But you could also have exact. You don't need to approximate. You just decompose into many gates using these general rotation. If you allow these angles to vary continuously. Okay. Let me see. There seems to be something in the chat. Okay, so let me read the chat. Okay, let me from the last. Okay, yeah. Why was alpha set to 0 when first qubit is 0 on the first of U1? So it's just the U1 alpha. The question is why U1 alpha act on 0 is 0, because this is 1. So that's this one. Okay. Why is V dagger not activated when it's 1, 1? Okay, somebody answer that because CNOT turns 0, 1 to CNOT 0, 1 turns 1, 1 to 1, 0. Okay. Yeah, okay, let me go back to there was one question asking the 1, 1 case, right? If this is 1, the CNOT would turn the 1 here, right? You follow through with 1, this would get turned 0. So 0 does not activate the V dagger. Okay. Okay. So this one is more complicated. So I would assign this as an exercise. It's probably worth going through that, but let me put this in context. So if we use this previous way to construct a Toffoli gate, right? We already have 2 CNOTs here, right? And in order to implement control V gate using this identity, for each control V, we need to have 2 CNOT. So I have to use 2 CNOT for this one, 2 CNOT for this one, and 2 CNOT for that one. So in the end, I would need 8 CNOT gates. And some of you probably know that in the current quantum computers, CNOT gates are the most noisy one compared to single qubit gates. So it would be useful to use fewer CNOT gates. This is one example here that you can use 6 CNOT gates. So 1, 2, 3, 4, 5, 6. So 2 fewer than the previous construction. Although the previous construction is general, it's not necessarily restricted to the Toffoli gate. This particular circuit identity gives you CNOT's implementation of Toffoli gate. So I won't go to the detail, but I would assign this as an exercise. The first, but you would use the hint that I have here. At least this is how I understand that. You first look at this block and you use what I did. So if it's 0, 1, 1, 0, etc., you check. You can first check that if the first bit is 0, the action on the 2 and 3 is really identity, okay? But when the first bit is 1, the action on 2 and 3 is a control operation, which if you use this identity, you find that it's control minus I times Z gate, okay? And if you want, you can then use the phase, right? This is a constant phase. You can put it here, so it'll be a 1 minus I gate. But because it has a control that there in the first bit, so this is a S dagger. So basically, I'm using this equality. I am using. Oh, sorry, it's saying it's here. I'm using this equality here to bring the phase to one upper level. Okay. And if I look at the other block that I indicated in the red dash box, this you can see that this is a control S gate. So S is diagonal 1I. Okay. It's really just simple checking when it's 0, it should be identity. When it's 1, it's become a S gate. So you go through the similar calculations that I did previously, and you find that these two cancel. These two cancel. So it become, these two blocks become a control Z gate, and then you use Hardeman gate, it turn it into control X gate. Okay. So I would assign this as an exercise. If you can go through this, verify this, then I'm sure then you would understand what I did here previously in this slide and the previous slides on the circuit identity. So I mean, at some point you have to go through this and verify at least once in your lifetime, so you have a better understanding. Okay. Any question? You may ask, is this the optimal? I'm not sure, but there is a paper showing that you need to have at least 5 2-qubit gate for Toffoli. So they're using 6. So it might be possible that there's a 5-qubit, 2-qubit gate You can look at this paper. Yeah, there are more construction or more recipe if you want to have many control bit. For example, here you have 5 bits used to control an action U. It's in general not so easy to construct, but there is one simple way. If you have extra work qubit, they are initialized in 0. You use these additional qubit that would allow you to just use the Toffoli gate and the control U to realize the phi control and on this U gate. Okay, and if you don't want to use the word qubit, it's more complicated, but it's possible. There are some exercise in the book of Nielsen and Tron that you can look up. Okay, so any questions? I'm turning into Qiskits in the following. So I'm just listing the gate that some of the gate that you can use in the Qiskit. So I will show the notebook, but the U3 gate we just introduced. So there is a theta and lambda are in the exponential, the phase, and phi as well. There's also a U2 gate, meaning that if you don't want the arbitrary rotation, you basically set the first angle to pi over 2 as a reduced. So they call this U2. 3 meaning that there are 3 parameters, 2 meaning that there are 2 parameters that you can use. U1 is the simplest one. It's just really a phase shift. Identity gate, it just write as IDN. If you want, you can also write U0. This actually should be U. I actually flip this. It should be U10. Okay, so maybe they have I need to check whether there's a U0 delta, but that's basically identity. Okay. The standard gate, poly gate X is written as XYZ, Hadamard, lowercase h, base gate S. Its inverse is S dagger, but you write SDG, T, and its inverse T dagger, PDG. There's also rotation, XYZ rotation, X rotation on which qubit and some angle. You can also have Y rotation, Z rotation, etc. More gates, these are multiple qubits. So the reason I list here is that this is basically sort of a table that you can look up when you are trying to use gate. And this is also sort of the catalog of the multiple gate. You have a control node, CX. You could also have a control Y, control Z if you want. But you know the control Y, control X, control Z, they can be transformed, right? So one example of this control Z that we talk about is really, you can use control not, but you use Hadamard gate before and after on the second qubit. So maybe an exercise for you is to see what the control Y, how do you get control Y from what gate before and after the X. So that could be an exercise. You could also have control Hadamard. Remember, if you recall that I have this W gate, which is Hadamard times Z. Yeah, so this is control Hadamard. It's close, not quite. You need to have another control Z to get this control Hadamard Z gate. There are more gates, so I won't go through all these. There's a swap gate, Toffoli gate. It's already implemented in the Qiskit. Okay. Other operations include also measurement. So at the end of the circuit, you need to read out, you say, I'm going to measure which qubit, and the classical outcome will be stored in what classical bit. There's also the reset. I think it may not be available in the real machine, but in simulator, you could do that. There's some conditional operation control if you measure a qubit Q, which read out to be C, and I want to apply the gate if that C is 0. Okay. So before I turn to the Qiskit notebook, I want to explain this Euler rotation and the U3 gate. So you probably learned in your mechanics, if I have two sets of axes, so let's say the capital X, Y, Z versus the lowercase x, y, z, they are arbitrarily oriented. But through rotation, a sequence of 3 rotation, you can bring the red axis to align with the blue axis. Okay. How many of you have seen this in your mechanics, classical mechanics, or any other mathematics? Yeah, please raise hand. Okay, quite a few of you have seen this before. But let's review this, and we're going to turn this into the gate. So first, for example, this is U alpha beta gamma. So we're going to define rotation, which is first z rotation with respect to the lowercase z. So if you using this as the axis and you rotate by alpha, so you rotate by, so let me see whether you apply gamma first and then beta and alpha. Let me see. To bring that, you rotate with respect to z alpha angle. So this would bring the y-axis to align with the n. Okay, then you rotate with respect to n. So when y is aligned here, the x would also be rotated. Then you apply the rotation with respect to n by some angle beta. This blue z-axis aligned with red z-axis, right? Okay. Yeah, so y was aligned with the n, and then you rotate with respect to capital Z by gamma. It's indicated here, so then all the 3 axes will be aligned. Yes, it may not be, you probably have to look at it carefully. And I might have said the wrong sequence, but that's the, yeah, some question? Somebody raise hand. Okay, so, but the idea is that by these, a sequence of 3 rotations. So first rotating by alpha with respect to the z, and then rotating with respect to the n by beta, and then rotating with respect to capital Z by gamma. You can bring all the 3 axes together. Was there a question? Yeah, it's not easy for me to see the chat. How to raise hand in Zoom? I think it's go to participant, and then you have more, and then there's some up, some down. Clap there more. I only see the, yeah. If you know how to raise hand, can you, if any of you knows how to raise hand?
Yeah, I think it's basically what you said. Just go to the participants, then on the then there will be a row of signs. Then you can...
Yeah, I only see some up, some down, and claps and coffee.
You can't see it because you are the host.
Oh, I'm the host, so I cannot raise hand myself. That's okay. That makes sense. Okay. So basically, yeah, by this sequence of 3 rotation, I can bring the red axis to align with the blue axis. So it may not be clearly shown. It's hard to draw. These XYZ, they're orthogonal. The blue XYZ are orthogonal and red XYZ, they are orthogonal. But the 2 frames are rotated with respect to each other. But it's always possible to bring them to align by such a sequence of rotations. So in the end, you do some manipulation. For example, a rotation with capital Z by gamma angle can be done by rotation with respect to the little z. But you first bring this back and then do rotation. And after you do the rotation, you bring it back, okay, back to the capital Z axis. So if you use that, you can rewrite this rotation. The reason is I want to replace these 2 rotations because they are not rotating with fixed frame. Right? N is something intermediate, and I want to rotate using the rotation with respect to 1 frame, like lowercase xyz. If you do these, replace the rotation by the lower z rotation, you can bring these u alpha beta gamma into this sequence. So you first acting the z, lowercase z by gamma, and then y by beta, and respect to z by alpha. Yeah. So additionally, if you may have an additional phase. So this is an arbitrary unitary group. So this is a unitary group. So this is U2 if you want. Okay. So if I do that and I expand it out, so Z rotation, remember it's minus I alpha and sigma Z over 2, right? Z rotation. I talk about the rotation. And Y will be beta sigma Y over 2. Basically, 1/2 of the polymatrices are the generator of rotation. Okay, so you do that, and then you just combine everything. In particular, the IBM U3 gate. If you multiply all these, this is 2x2 matrix. So the choice of the IBM U3 is such that this element is real. So they want to have a phase chosen so that this part is real. So that's and the choice is delta is the sum of the alpha, the average of alpha and gamma, and beta basically is the main rotation, the y rotation. Yeah, by choosing this, you get a U3 gate. Okay, any question on this part? You might need to go back to see how the 3 axes can be brought into align each other by looking at this diagram. Okay, so yeah, measurement, I'll talk about this already, but I want to actually discuss the scenario that we usually measure in the 0-1 basis. What if we want to measure in some other basis, like psi basis, right? So remember, if we have a wave function we want to measure in a 0 and 1 basis, and these are the probability, right? P0 will be this, P1 will be that. But if we want to measure in this rotated basis, so for example, we want to measure in the plus basis or minus basis, we know we can first do a Hadamard, right? We can do a Hadamard before we measure 0 and 1, okay? So in this regard, so the general basis, in order to measure that, we can apply the inverse of that before measuring in the 0-1 basis. So this, it's easy to remember. So because the xi plus, xi minus, you write in these broad basis, it's the same as 0, you dagger on that. Okay, that's why you apply dagger and then you perform measurement. Okay, this is represented in this diagram. If you want to measure in this basis, you can do the inverse rotation and measure in the 0-1 basis. Okay. Okay, there's also the question that if I have a single qubit operator, for example, and I want to actually measure and then leave the output in the eigenstate, and this is how you do that. So you would send in this state, but you need to be able to do a control O action. But this, as we see before, you might be able to use the circuit and using control knot and 1 qubit rotation to achieve that. But this certainly get you to that. So, but I want, let me maybe leave this as an exercise because I want to spend time on the Qiskit notebook. But before that, there's one important piece of measurement property. So this may be easily illustrated. So measurement can be moved to the end of the circuit. For example, this is the, if you remember this is actually the teleportation. I write in terms of circuit. This is the Bell state. And in your homework, you show that this is actually Bell state basis measurement. So meaning that this would be teleport to 3 to here to, sorry, it's using Q2. So the qubit 0 is teleporting to Q2, but you need to have some conditional application, condition on the measurement. So these two lines representing classical formations sent by Alice in principle. Although in the circuit way, we didn't separate into Alice and Bob. But this actually is equivalent to postponing the measurement till the end. So, but you use the control operation. So you see, you use classical control X, but this classical control is a measurement outcome of the qubit 1 here. You could replace that by a control NOT operation. This is control Z, controlling the measurement outcome of the 0th bit. So that's control Z. And then you can postpone till the end by measuring these 2 qubits. So this would have similar, if the same effect. Okay. Any question on this point? Maybe let me skip this first. Yeah, so in the Qiskit documentation, they have a lot of tutorial. Basically, if you're interested, you can go through these by yourself, but I'm just showing the summary of the quantum operation. So I'm going to open open the notebook. Let me share the screen. Okay. Anyway, this is the website that they place the tutorial. So if you click, this is the event. So if we go to the tutorial, you go to the circuit, you go to the 3, you can download these files. So you see in the content, this basically have some basic introductions and the gate, right? This is the U3 gate that we have seen. So they show the single-qubit gate. So what they usually do is you need to declare quantum register and then a quantum circuit using the quantum register. And here, this example, use a U3 gate. So basically what you do is set the circuit dot the gate operation, circuit QC.U3, and these are the angle that they want to apply. These are 3 angle, and this is the Q is the qubit. You can draw this, okay, so you can draw that. That's Q0 with the 0th qubit, apply this U3 gate, okay. You could run, you can execute this quantum circuit using the so-called back end. So what they do here, you need to select which device or simulator. In this case, they use a unitary simulator. And then they run this. They can, once it's done, you can say, I want to obtain the result just using these function call, and then you get the unitary. This is the QC is a circuit. This is just representing how accurate you want to represent this. So it would show the matrix of the unitary. Okay. So perhaps I'm going into too much detail here, but this is where you can download the notebook, but I'm going to post this in the Blackboard. So I'm showing their GitHub page, but if you download it, depending on what you use, so I can open, remember last time I told you there are at least 2 ways you can install the Qiskit software, or you can use this CodeCal website. This is, I download that and then I download the notebook and then upload it to this website. So you can execute that. So import the plotting function using NumPy, etc., Qiskit. These are standard, so you don't need to worry. You just need to import these packages. You choose a backend. They call this backend. Yeah, there are some description. You have already seen that. You can really run that. So in the draw function, if you use you put NPL, then this has a better, nice looking than the text drawing. So let me make sure, can you all see my page, open the code in the code calc? Okay.
Yeah.
Yeah. And I want to make sure that when I switch the website, you can still follow that. Okay. So this is just showing that you can do. So yeah, you can really run this. So I think I run this. So you just press Shift Enter, then you will run the command, then you execute that. Okay, you could draw this. Okay. Yeah, so you really have these as a tool that I developed. So it's probably a really good time to learn quantum computing, because in the past, there was not such a software for you to learn, but now you have very useful software and visualization. So you can try all the gate and show how the actions on the qubit, etc. And there are more gates. They illustrate how you apply these gates. Yeah, even the T gate and rotation. We talk about this rotation. You can draw this circuit diagram. Because at single gate level, it's really not much. But once you have combining this into a circuit, it would be you can have more things done. Okay. Yeah, I'm just browsing through this. So I encourage you to just download, and then upload to your favorite place that you can run, and then just see what it comes out. So there are also 2-qubit gate, swap gate. Swap will swap the state, and you can really swap them. You could run this and see the unitary representation. And there are also other. This is the Toffoli gate.
Probably need to let them know the endianness of qubit representation.
I'm sorry, what you want me to do?
The endianness of the qubit representation on IBM.
It's okay. We get to that. Like, you mean this, the ordering?
Yeah.
Yeah, this is fine. I mean, they order in a way maybe different from other convention. So they would use the qubit 0 to the far right, and qubit 1. The highest qubit number would be to the far left. So that's how they would label. But most of us, including the books, they label qubit 0, 1, 2 in the reverse way. But in the Qiskit, there's a way you can reverse the circuit. So that's not really a big issue, but just need to be aware. Okay, there's also measurement, reset, conditional operation. You all see these. This is a classical control, but you can really just use control gate and at the end measurement. Okay, so, and then you can initialize the qubit, etc. Yeah. I want to see if you have any questions. Okay, so if not, let me switch back to the slide. Okay, so maybe I'll get back to the previous slide maybe next time. This particular topic on Clifford gates, but maybe let's do a poll. I hope you can get comfortable using these software tool. But let me bring out the poll before we end. Okay. Can you take 1 minute? So let me know. My goal is to have everybody comfortable with Python and Qiskit. It's not necessary you need to write codes from scratch, as long as you can take the existing codes and modify and play with it to have better understanding. I think using these software enhance your learning experience. So it's worth doing that. And besides, there are some benefit, right? If you are really good at programming in this or other framework on quantum computing, there are job markets. Okay, so most of you have voted, so let me end the polling. and share results. Okay, at the same time, let me copy this. Okay, so I think most of you feel comfortable now. So I guess there's only one person that answered no to the first question. Yeah, so I would like to help you, and maybe other people could also help to make everybody comfortable with running IPython and Jupyter Notebook. And then, by the way, I think Wenhan wrote a tutorial, really short tutorial showing you how to install and run. So I uploaded that document, Word document, into the Blackboard. You can take a look. If not, you can ask Wenhan. Maybe Wenhan, you can raise your hand so people knows.
Hello,
Okay,
I'm Wen
yeah.
Han. Yeah.
So if you have a question, you can ask Wenhan, and maybe you, Shen, you could also help other people if, yeah. And I think there are a few other that I know that they also know Qiskit, like Bharat, maybe Anne also, yeah, Anne also knows. It'll be useful, really, that I hope that everybody in this class knows how to use that. Okay.
Yeah, anyone can message me or talk to me if you want help with Qiskit. I'm Bharat.
Okay, so let me keep the annotation and then paste this. Okay, it's close to the end. Yeah, so let me know if you have any questions on today's lecture or how to install Qiskit or run Qiskit. I think there are people who know these, so maybe I could list their names in the Blackboard. If you have a question, you can also message them. Yeah, so, or if you really need help, send me an email. Okay, if not, then we can end today's lecture here and I will stop recording. Yeah, you're free to leave.
Thank you.
Thanks.
Thank you.
How do I stop the recording? Hello, trying to stop the recording. Stop recording. Okay.